perform our lab number 2 using PBT simulator. The title of our lab is the saturation pressure of a binary system. Okay. In our lab number 1, if you remember, we performed the PBT studies of the single component, and that was a CO2. But this time we are going to study the mixture of the phase behavior of the mixture of two components. Okay. And what we are going to recover is actually a pressure versus composition diagram. And if you remember from our lecture, we were discussing if we have the mixture of two components, we can plot pressure versus composition diagram for a constant temperature, at which we start from the left where we have a 0% of component A, meaning that we have 100% component B, and then we try to find the bubble point and dew point pressure of that component. Since it's a pure, when we have 0% of A, definitely it's 100% component B, so it's a pure component B, the bubble point and dew point would be the same, and it's equal to the vapor pressure. That was our lab number 1. So we'll get the first point. And then what we'll do, we start generating different mixtures by, let's say, adding 10% of component A with 90% of component B, and then finding the bubble point and dew point pressure of that mixture. How to find that? Exactly the same way that we found the bubble point and dew point of the single component. We start from the system at the liquid phase, and then we start expanding the liquid till the first gas bubble comes out, and then we collect that pressure as a bubble point, and then we continue dropping the pressure till we get to the dew point, and then we collect that pressure as well. In this case, since we have a mixture of two components and it's not pure, so the bubble point pressure will not be the same as the dew point pressure. Okay, and that's basically what we have here. The blue star stands for the bubble point, and then the red star stands for the dew point. When we have this two, we generate another mixture. Let's say this time 20% of component A and 80% of component B. And then we find the bubble point and dew point. And we continue till we get the 100% of component A. Again, in the case that we have 100% of component A, that's a pure component A, and the bubble point and dew point would be the same. So this bubble point line, which is basically a line connecting all these bubble points, and the dew point line, which connects all these dew points, they meet at this point where we have 100% component A. Okay, so we will generate this pressure composition diagram, and we know in the left side of the bubble point, we will have bubble point line, we will have the liquid. Inside the two phase, we will have gas and liquid, and outside we will have the gas phase. So that's the idea. That's what we want to obtain doing this lab number 2. For lab number 2, the mixture that we are going to study is a mixture of CO2 and butane. Okay, so we are going to study mixture of the behavior of CO2 and the butane mixture. However, there is one problem, and that problem is, if you remember, even for the single component CO2, it was very hard to find the dew point. Okay, because the visual cell had a very specific, volume. It was like the volume was limited, and even a small amount of liquid, we couldn't really get to the. We did able to get to the dew point, but in some cases, depending on the temperature, even a small amount of liquid, we will not be able to evaporate with the size of the visual cell that we have. Okay, so what we are going to do here is to use the behavior of the property of the equilibrium tie line. If you remember, we said we discussed the equilibrium tie line, and we said these tie lines are the parallel lines with the x-axis, where these lines are connecting the saturated liquid and saturated gas of the mixture at a specific pressure. So what we can do actually here, because in this lab, in the PBT lab, we do have a luxury of you having the gas chromatograph. So what we can do, we can find a bubble point. That's easy. So because the liquid is compressible, it's slightly incompressible, we can say, and the liquid is incompressible or slightly compressible. So small change in the volume will lead to huge change in the pressure. Therefore, finding the bubble point is very easy. The liquid cannot expand that much. It expands a little bit and then it starts vaporizing. It starts going to the gas phase. So we can find a bubble point. So when we find a bubble point, that's basically our saturated liquid. Okay. At that point, what I can do is I can use the gas chromatograph and I can find what is the composition of the saturated liquid. Okay. At that point. So at that point, it's going to tell me what is the composition of the liquid and what is the composition of the gas. So I can find the percentage, the composition of the, let's say, component A in the liquid phase and component A in the gas phase by performing the gas chromatograph at the bubble point. So instead of using these stars, like the blue and the red stars, I can find the blue star, and at that time I can use the gas chromatograph to find the corresponding blue circle on the saturated gas line. Okay, so the blue circle is basically the saturation, the composition of the component A in the gas phase at this specific pressure. So we have the composition of the liquid at this specific pressure and composition of the gas at this specific pressure. So we can use these 2 points to generate this phase envelope, because I know the small blue dots also fall on the dew point line. So instead of using the red stars to generate the dew point line, I'm going to use the blue circles to generate the dew point line. So one more time. Generally, to find this phase envelope, for every mixture, we find the bubble point and dew point. And then connecting the bubble point line and the dew point line, we will be able to get the phase envelope. However, since finding the dew points are difficult, I'm going to use the definition of the tie line. So every time, for every mixture, I find the bubble point, and right at the bubble point, I use the gas chromatograph. So if I run the gas chromatograph at the bubble point, it gives me the composition of the gas. Okay, so I know how much of component A I have in the gas phase. It also gives me how much of component A I have in the liquid phase. So I will have the blue star on the bubble point, and I would have the blue dot on the dew point line. So instead of using these stars to generate the dew point line, I'm going to use these blue dots to generate the dew point line. Okay. So when I do that, I will have this saturation envelope of a mixture of 2 components. But there is a small problem, and that problem is, if you can see the first point on the dew point that I can get, actually the second point, because the first point would be right here. The second point is right here. So there's a huge region here that I don't have any information. Okay. So I don't know what would be the curvature here. So to make this curvature, what we are going to do in this lab is to use a very, very small amount of liquid and try to find the dew point pressure. We know the bubble point pressure and the dew point pressure is a function of, it depends on the mixture. It doesn't depend on the quantity. So 10 cc of the mixture of CO2 and N-butane would have the same bubble point at the same constant temperature as 1 cc of the mixture will have that value. Okay. So since it's not a quantity dependent, I'm going to perform one experiment only on a very small amount of mixture and try to find the dew point. Even with that small amount, I might not be able to get exact dew point, but I would be able to get some point very close to the dew point. Okay, and I can use that to basically as an indication of how this curvature of the curve, how the curvature of the dew point line at this region would be. Okay, so as we do the experiment, this becomes more clear. So again, we are going to have our PBT lab simulator. And this time, if you remember, if you look at the graph, you will see one of these tanks are out of the cabinet. So this tank, which is now available for us to perform the lab. Okay. So what we are going to do is we are going to have the N-butane individual cell, and then we are going to add CO2 to this N-butane and generate different mixtures. Okay. So here what we will have is the percentage of the CO2. We are going to add the CO2 and generate a mixture of 10% CO2, 20%, 30%, and all the way to 90% of the CO2 in this visual cell. And every time that we generate the mixture, we are going to find its bubble point. And right at the time that we find the bubble point, we are going to use the gas chromatograph to get the information required. Okay. One thing is to just remember, since now we are dealing with the mixture of 2 components, Every time we generate the mixture, we need to shake the cell, because if we don't shake the cell, the system will not reach to the equilibrium, and all the pressure values that we are reading would be wrong. Here we are not interested to find the bubble point volumes or something like that, so we just need to have these the bubble point pressures for different mixtures and the composition. So I'm not worried about collecting the data regarding these bubble point calculations. Okay. So there are two ways of doing this experiment. The way that we are going to do is called the total CO2 volume or cumulative volume. There is also another way of doing this experiment, which is called the incremental CO2 volume. So what is the difference between these two? In the total CO2 volume, basically, if you remember, we said we have N-butane in the cell. Okay, I'm not going to play with the N-butane. I have a known volume, a known pound mole of N-butane in that visual cell. So I'm going to add, let's say, A amount of CO2, and I generate a mixture of 10% CO2 and 90% N-butane. Okay. When I'm done with this experiment, there are two ways to go forward. One way is to just dump everything out. So I can just dump that mixture of 10% CO2, 90% N-butane out. I start with the fresh tank with fresh N-butane. Now I can say, now I wanted to do the 20%. So how much CO2 I need to put to this 100% N-butane to make it 20% CO2, 80% N-butane. When I'm done, I dump the fluid, come back with the fresh N-butane, and say how much I want to add to generate 30% mixture of 30% CO2, 70% N-butane. So this is called total volumes, like the cumulative volumes. Okay. So this is easy performing with the PBT simulator, because every time you find a bubble point, you can just exit the program and come back again and enter the program again. You will have the fresh N-butane and you can do the experiment. Okay. However, this is not practical when you are doing in the lab, because every time you generate a mixture, you just don't dump it and just waste all the mixture and come up with a new mixture. Okay. In the actual lab, what we do incremental. So when we generate a mixture of 10%, let's say CO2, 90% N-butane, we say how much more CO2 I need to add to make this 10%, 90% being 20%, 80%. And then when I have 20%, 80%, how much more CO2 I need to add. So I keep that fluid and I go forward. But here, as I said, because it's easier to just exit the program and come back again, we're going to use the table 4A. So in table 4A, there are a couple of things that you need to pay attention. First is the temperature of your experiment. Okay, so there are 11 different temperatures. So we are going to do temperature group 1, okay, which is temperature 1. Okay, that's what we are going to do. This information, which is the temperature, the moles of N-butane, and the temperature in degree Fahrenheit, this is in degree C and degree Fahrenheit. These are fixed. So I know what's the mole of N-butane in the cell. I'm not going to change the N-butane. I'm not going to add N-butane or remove N-butane. I'm just going to add CO2. So the number of moles of N-butane is fixed at a fixed temperature. So this is, let's say this is 0.1025 cc or pound mole. This is pound mole. Or moles. This is moles. 0.1025 moles of N-butane presented in that cell. I'm not going to change that. So this is fixed number. If I'm going to do the experiment at this temperature, 71.6, these numbers, 0.1, 0.2, 0.3, all the way to 0.9, are the mole percent of the CO2. So if I want to make 10% CO2, then I need to add 0.570 cc of CO2 to the visual cell to generate a mixture of 10% CO2, 90% N-butane. If I want to generate a mixture of 20% CO2, 0.2, then I need to add 1.282 cc's of CO2 to this N-butane, and so on and so forth. So if I want to generate 0.9 or 90% CO2, 10% N-butane, I need to add 46.137 cc's of the CO2 to the visual cell to generate that mixture. Okay, so these numbers again, 0.1, 0.2, 0.3, 0.4 is the one that we pick. I want to generate a mixture of 10% or 20%. And the number beneath is basically giving me the volume of the CO2 required to generate that mixture. Okay, so for this experiment, we are going to do group 1, temperature T1. But to use this table, what you need to prove one of these numbers, okay, one of these numbers in the table.